Okay, we start the final week with this course. That's mandatory, you might say. So the final part, that is turbulence. And that's one of the three parts you then can choose on the exam. We are missing the turbulence. Also, I want, in the end, to touch verification validation. Actually quite essential for any CFD simulation. You can't really do anything with simulation unless you have validated and verified your results. It's pretty worthless without it, so this is quite essential actually. But it shouldn't take too long. So I guess we'll be finished by tomorrow with the theory. Then next week, for those of you who want, we play around with OpenFOAM. So then you bring your laptop. Either you have Linux and OpenFOAM installed, or you have a laptop that is possible to boot on a USB memory stick. So then you have to check your computer, how to enter your BIOS, how you can change the order of the boot sequence, that he starts with the USB first and then internal hard drive next. Okay, the turbulence material you have been given is more or less these two, and regarding the exam, it's the first one that's important. So we are spending a lot of time on this one. Second part here, that's sort of more examples. It's a bunch of articles that we are going to go through. Look into some examples, some cases where we know the classical turbulence models have problems, and then see how that can be improved by using more advanced turbulence models. You have also been given here lecture notes from Helge Andersson, sort of a little more in-depth material when it comes to turbulence models. So this is then just for reference. You don't have to go through it unless you want to. Also a small article that I will have a little peek into when we start looking into the really advanced turbulence models, large eddy simulation, and direct numerical simulation. So let us begin. Here is something I found in a book of chaos theory. So you have the complexity, the number of unknowns here, all the way down to continuum, and starting with the simple problems and then more and more nonlinear problems. So the very easy problems you find up here. That's not a problem. Going to continuums, waves, and all the way down here to viscous fluids. And we're talking laminar flow. And chaos, strange attractors, fractals, whatever, fairly known. So the frontier, research frontier, they have drawn a line here. So inside down here, we are in trouble. And the most complex, the worst of any problems, is all the way down here. It says life. And then just above it, you find turbulence. I would say these two should be flipped. Turbulence is much worse. It's really, really nasty. I mean, Einstein started looking into turbulence and he gave up. So turbulence is nasty, very nasty indeed. We don't have a really good definition of turbulence, so it's more like the definition you have on pornography. You can't really define it, but when you see it, you know what it is. So it's sort of the same with turbulence. You know what it is when you see it. But as a definition of turbulence, we demand that the turbulent flow has all the following characteristics. It's going to be diffusive. It's going to mix up a lot. So the mixing effect within turbulence flow is many times larger than for any laminar flow. It's a large Reynolds number phenomena, and here what's large, depending on the problem, of course. Pipe flow, 2,300 for flow around objects, some 100,000s. Flow around, along a flat plate, 1 million. So that depends on how you define your Reynolds number, of course. Vorticity, oh yes, you have a lot of vortices, and in turbulence you might think of sort of the biggest scale that you have in a problem. If you look at a waterfall, for instance, a river tumbling over a cliff, the largest scale that you have, the biggest vortices you can have, will sort of be the biggest dimension in the problem. And then in the Navier-Stokes we have some nonlinear terms starting to break up these large vortices into smaller and smaller vortices, and so on all the way down to viscosity. Then you are just producing heat. So the vortices is going to be broken up into smaller and smaller vortices. Not necessarily only a one-way street there. You might have smaller vortices joining together, constructing bigger ones. So it's a very complex picture, but for the main part, the energy goes from bigger vortices to smaller and smaller vortices, all the way down to the smallest possible little vortex you can see in your flow. It's a three-dimensional phenomena. You need all three dimensions to describe it correctly. It is dissipative, it's stealing energy. In a pipe flow, if you have a laminar flow, for one given driving force, one given pressure gradient, if the flow all of a sudden flips and becomes turbulent, the velocity is going down. It's much more energy demanding flow than a laminar flow. Of course, you have a lot more action. We believe it's a continuum. So that goes for the entire Navier-Stokes as well. We believe that we can describe it using a continuum media. We don't have to go all the way down to molecular behavior. And it is transient. So a steady state turbulent flow, no, you don't find it in nature. You have a lot of flows involving several of these characteristics. Say you have a laminar flow around a cylinder, then you will start with this vortex shedding. So you have a nice von Karman vortex street behind a blunt object. That is not turbulence, that's still laminar. So it's transient, not really 3D, it's two-dimensional. You have a lot of vortices. Reynolds number may be a little bit large, but you don't have all of them all together. So it's more or less a two-dimensional flow, hence laminar, although unsteady. So we believe strongly that the Navier-Stokes will describe turbulent flow. You don't need any other equation. The Navier-Stokes describes turbulence. Nobody has proved anything else. So yes, we do believe that. So what we are going to peek into is the different parts here. The first part, that's the turbulence 1 that you have been given. It's a rather old one actually, something that Professor Andersson wrote for a conference within hydraulic machinery, turbines, pumps, stuff like that. But it's actually a quite okay overview over what we are dealing with, and a couple of examples there where typically this standard turbulence models where they have problems. Then we have 3 different articles describing cases where you need a little bit advanced turbulence model to describe the physics. Number 5, that's actually something we wrote for a mathematical journal about direct numerical simulation and large eddy simulation. So that is more or less the topic that we are going to deal with. The preface we skip. So the first part here sort of focus on then hydraulic machinery and how we are dealing with turbulence. So before we dive into this one, I will give you a quick overview over the different turbulence models and what family they belong to. Because this one, he dives more or less directly onto a quite high level, so you need an overview over turbulence models before we begin. So let's start with turbulence and turbulence models. The simplest family of models we can call correlations. So you start simulating something and you are running without any turbulence model, and then everything explodes. So what do? Well, a very simple model will then be to say viscosity is now viscosity multiplied with a big number. That's a turbulence model. Then what actually you are doing is you are reducing the Reynolds number to something that becomes laminar, and then you have control. So it's a very bad model, but it works. But of course you are now simulating a totally different fluid than what you were thinking. So very bad model. More engineering for correlations. You have Bernoulli with losses. So like what do you have in Bernoulli? You have a delta P loss over density. There you'll have a function, friction factor F, length over diameter, V square half, and so on. And this friction factor then can be found from a Moody diagram or simple correlations like Blasius, Prandtls. You have several of these where you have a friction factor depending on typically the Reynolds number, but also maybe on the roughness of the material inside a pipe. You have several of these correlations depending on the problem, of course, pipe flow being sort of very engineering important. Very simple model, but hardly anything accurate. You have a second family, integral methods. We don't have that many of these, but some. You have the von Karman. He has an integrated momentum equation. Momentum equation. You have some theory from boundary layer. You can integrate up some similarity solutions, finding the skin friction depending on based on some integral formulation of your equations. Stuff like that. But again, engineers, simple problems, and he doesn't describe it so accurately. for the given problem, for a certain problem, these integral methods may be quite accurate actually, but that's only so and so far you can come with these methods. So quite a narrowed quite limited limited number of problems actually. Then we have a very, very big family, and here is what we are going to deal with: the Reynolds averaged Navier-Stokes Rans methods. So that's a very, very big one. So I will go into a little bit detail how you create the Reynolds averaged Navier-Stokes. And here we are talking subfamilies. You will have algebraic equations, so quite simple models, and you find several of these actually quite useful. Some Prandtl's mixing layers. You will have an eddy viscosity given by something gradient of your inside your simulation, stuff like that. So you just sort of increase the viscosity. You add an eddy viscosity, for instance. That's quite typical for these algebraic equations. And quite a big family of these, Sebastian Smith, a whole bunch of them. But it's only an algebraic equation. So that means if you have a turbulence in one spot, then you have to deal with it there. It doesn't move around. There's no transport equation. So the next one, then you are talking one equation models. There you have one transport equation, and by a transport equation, we'll come back to that later, they will typically start with the total derivative of something. And for one equation models, you have several of these. A transport equation for the turbulent kinetic energy, transport equation for the eddy viscosity, stuff like that. So, but only one transport equation. Spallar-Almaraz, very popular one. Only one transport equation, but it can describe several turbulent problems quite decent. Then, more advanced, we have two equation models. And here, of course, you find the most popular, K epsilon. But of course, you have others as well. K omega, omega being sort of a turbulent frequency, and you have others as well. So here you find many turbulence models. So next to the Navier-Stokes, Navier-Stokes being three transport equations, one for each velocity component. Then you have two transport equations in addition. Then we will have what's called an ASM, algebraic, what should we call it, stress model. That is then an ASM. So to define what an ASM is, we first then have to define the next one. Then you will have what's called a full Reynolds stress model. Reynolds stress model. And in general, a full Reynolds stress model, he will be 7 transport equations. 6 for the different Reynolds stresses and 1 for the dissipation. So there you are talking research. That's rather heavy, both numerically and a lot of modeling to handle these. So very, very tough indeed. The ASM, that is sort of an expansion of the two-equation level. So you take the solution from a two-equation and then you play around only with algebraic equations to find the different Reynolds stresses. So we'll come back to that one, how that one is made. The industry will typically stop here. They will say you have used K epsilon. Wow, that must be beautiful. Then it's the pure gospel. Of course, they believe anything when it's a two-equation model. Then it has to be very, very nice, very correct. Researchers, they will start somewhere down here, of course. So these are not for researchers, I would say. Then we have family number 4. That will now be large eddy simulation. And finally, direct numerical simulation. So here, LAS, DNS. So with this family, it becomes more and more advanced, more and more complex, more and more heavy to do a simulation, but it should be more and more accurate. So in the end here, you have no turbulence model at all. You solve the entire Navier-Stokes as it is, requiring then that you describe everything that goes on in a flow. So here you are talking a full three-dimensional transient flow. Even though your problem is one-dimensional, it doesn't matter. You have to do it in full 3D and it has to be transient. So that one is extremely computer demanding. With a large eddy, you admit that I can't really resolve everything. The smallest turbulent scale is very, 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 very small. So here we say we cheat. We have a cell system, a mesh that is too big. So you should have some activity inside your computational mesh also that you're not capable of describing them. Then you use a very simple turbulence model to describe the turbulent activity inside your mesh systems. But he covers the large scales, the large vorticities, the large turbulence motion. But inside the cells, you use a very simple model, typically something like this. Just a very simple model. They have tried using more advanced turbulence model inside one single mesh, but it's actually not worth the effort. So very simple model inside your cells. That should be a quick overview over turbulence and turbulence models. So we are diving into the Reynolds averaged Navier-Stokes, and we are going to focus on this level because this is typically where the industry stops, and it's a lot of cases where this is not good enough. So that's what we are going to focus on. Any questions so far? That's okay. So I will go through a little bit now how to achieve the Reynolds averaged equations. So here they sort of just start with claiming that the Navier-Stokes, we believe that it describes both laminar and turbulent flow. And of course, as you should be aware of, this boundary layer hypothesis, that yes, you may use laminar flow simulations outside the boundary layer. It should be okay. You can even use Euler codes if necessary, and then do something within the boundary layers. But that's sort of not so very accurate. So here we are jumping directly into the family of Rahn's methods. So how to achieve a Rahn's equation. How to find the Reynolds average Navier-Stokes. If you look at a turbulent signal, say you're looking at velocity as a function of time. So imagine you have a probe at one point inside the flow is just running, you are measuring the velocity, and you have a very good measuring system, something, and you will have a signal looking something like this. So here you have a lot of information. The flow may or may not be stable. It can change with time, of course, but all these rapid fluctuations, typically a turbulent signal. As an engineer, you will typically now say that I'm not interested in all these messy details. I'm interested in sort of the overall behavior. So what I want is a velocity looking something like this. So how to achieve that one? Well, we now say that this average should be now a velocity large u, which may or may not be a function of time. But how to create him? Well, imagine then you create here a sort of a time window, delta t of some kind. And then you say the average, the large u, the average velocity, is now the average just within that window. And the point in the center here then, the value here, u, will now be sort of 1 over delta t integral of u dt from a time something like this. You never define actually what this time window should be. So this is just sort of a philosophical concept that we keep in the back of our head. We don't have to define this time window, but what we then are going to do is the following. We say that the real velocity u can be split up into the mean part, the average part, plus, and then the fluctuating part. So we typically will have a little prime there to claim that will be sort of the small turbulent behavior that we are actually not so interested in if we want to find him. The real truth, okay, that is just u itself. And then, of course, you do the same split with everything. The real pressure, you have a mean plus the fluctuating pressure. For all velocity components, density, if that is a compressible flow, and so on. And now we are going to split up our equations using this mean and fluctuating concept. We need some rules of calculations here. So if I have any quantity A being a mean part plus a fluctuating part, so now you create what's called a time average. We have it here more or less. So this one you claim is a U time averaged. You use a bar on top to say time averaged. So that means here the time averaged of a quantity A will only be the mean part. Then the fluctuating part has been removed, of course. If you take the time average of, say, a derivative, whatever, dA, dx, or dt, or whatever, and a time average, then, of course, that will be the same as creating the average first, and then take the derivative afterwards. Mathematically, that should be the same. And of course, here you'll see you'll get back only the mean part. If you have a mean quantity multiplied with a real quantity, A, multiplied with an already averaged quantity, B, and then take the time average, well, of course, this one will now be just this part here, A, B, nothing more. The fluctuating part, since you only have one of them, will disappear. If you have something like this, two real quantities and then time averaged, then you're in trouble. That one doesn't disappear. And if you have a square and then averaged, also a problem, doesn't disappear. So that one you can't really split up. You can try a little bit. Well, it's easier actually to use an example. Say we have the beginning here of the Navier-Stokes, du dt, u du dx, v du dy. So there you have first three terms in the x component of the Navier-Stokes. Now insert the split and then take the time average. What do you get? Well, here you have time derivative of large U, fluctuating part, and then you'll have large U, U fluct, x derivative of the same, U plus U, and finally large V plus little v, y derivative of the same, v plus v fluct. Then you take the time average, and then you can sort of think you can take one large bar over the entire equation, but of course the time average of two added terms will be the same as to take them average one by one. And if you have derivatives, it's the same as keeping the derivative outside. So time averaging here would be something like this. Here we are in trouble, of course. And here also, you can't really split that one up so easily. So what do we get? Well, the first term, that's trivial. He will disappear. So here you are left with this one only. What about these two terms? Well, you sort of have no choice. You have to split it up. You can extract the mean parts, large U dx, and we can take the v as well here. V d, that was wrong. That was wrong. It's a small u that should be inside here. U plus u float. Like that. Then I have taken only the two mean terms from that one. And now if you start combining, if you take the mean here and the fluctuating there, they will always disappear. They will be of the type u d u fluct d x, and this one average disappears. When you have only one fluctuating quantity and then time averaging, he will disappear. So what's going to survive here is when you have only the fluctuating parts. So this one is going to survive. And same for the last one, v fluct d u fluct dy. They are going to survive. So this is what you get in addition inside the Navier-Stokes. On the other side, well, that's hardly any problem. You have the real pressure and gravity, if you like, and then double derivative with respect to x, with respect to y, and whatever. So there you see on the right-hand side, when you take the time average here, you are left with the mean pressure, and here only the mean velocity. You only have one of them. So these terms, not a problem. So there you will now get an entire Navier-Stokes, but only with the mean quantities, the mean velocity field, the mean pressure, except these two guys. So they are sort of in addition, sadly. So typically what we do with these, we write them on the form d dx j of u I u j fluct parentheses, something like that, and then time averaged. And these guys, that's what we call a Reynolds stress. And then we throw them on the other side of the equation sign in the Navier-Stokes. So they are actually accelerations due to turbulent motion. That's where they are born. But we will throw them on the other side and join them with the viscous stresses inside this term. So a turbulence model in the family number 3 is how to describe these Reynolds stresses, how to get a number inside the Navier-Stokes for these guys, now belonging on the other side of the equation system. Reynolds stress described by a turbulence model. So that is a turbulence model for you. That's his job, finding a number for these unknown stresses. The rest we know how to handle. The ordinary Navier-Stokes, not a problem here. And also now with the pressure and the viscous term, not a problem there. It's only these guys that's the pain. You can of course do the same with continuity, but continuity equation, well, that's not a problem at all. You will have only one velocity in each of the terms, divergence equal to 0. So there you will have an equation directly with only the mean velocities. What you also can do now is start playing around with the algebra. Here you have now obtained and Navier-Stokes. If we write it out completely, then we should actually do something like this. Equals minus minus, and then you'll have this guy, incompressible. I keep the density as a constant, but then derivative of the mean pressure, and then viscosity, double derivative of the mean velocity, like that. And then these guys time averaged. So now you can start playing around with the algebra. You can take this equation minus this one. And then before you do the averaging here, then you can sort of manipulate and find a transport equation for not the mean part of the velocity, but actually for the fluctuating part. That's possible. Not so interesting, but yes, you can do it. And what also you can do, take this equation here and multiply him with a fluctuating part. Then it's actually possible to construct a Navier-Stokes, a version of Navier-Stokes, now being an equation for this guy. So here you have plenty room to create new equations just by manipulating them. And yes, that's also something that we are going to have a look into. We are going to need transport equations for different quantities, so here we can actually write them out analytically and see how they look. Not that it's going to be very funny, because a lot of these terms here are going to be very messy indeed, impossible to calculate, but yes, it's possible to find them. Okay. That was the birth of a Reynolds averaged Navier-Stokes. Any questions to that one? Then we take a break.